with a talk by Roger Nelson about the study of psychokinesis.
Yes, I could say Kalimara, but it isn't morning anymore. And I don't know how to say good afternoon. But it's good to see you all. I've been asked to talk about the study of psychokinesis. You heard, fortunately, quite a few useful definitions from Mario earlier, and also some indications of the coverage that might be required or found in Fortini's talk as well. What I'll be talking about is mostly what we refer to as micro-psychokinesis, but there is a whole broad spectrum of other kinds of things, some of which you've heard about. People talk about haunted houses and things moving around. Spirit contact, who sometimes do things that are, in a sense, physical. Table tipping, or table turning, as it's sometimes called, where people sit around a table and try to make it levitate. Spoon bending became very famous because of Uri Geller showing it on television, and people all over the world, usually children, started bending their family silverware, much to everybody's disconcert. Many people, psychics who are advertising their wares, will attempt to move small objects like pencils or toothpicks, matchsticks, and so forth. And Fortini, I think, mentioned poltergeists. And they are, what that amounts to is objects lying around the room or sometimes being teleported from one place to another. And it's very often associated with teenagers. But I think you can see, here in the earlier talk, it's hard to study these kinds of things scientifically. So we bring our phenomena as best we can into the laboratory. J.B. Ryan may have been the earliest major experimenter producing laboratory research in the US, but there were people in Europe, Canagras, and also Hans Bender in Germany, a number of physicists in London, and so on. But the business of micropsychokinesis got its start into a really powerful future in the 1960s, late 1960s, when an engineer at Boeing Aircraft named Helmut Schmidt decided that it was a good idea to find out more about random numbers. Random numbers are important in technology, and he had some suspicion or intuition that it might be a good question to ask whether certain mental states could change the behavior of a device that produces random numbers. And so he built such devices, and he set them up with feedback. On the left, a picture of a person trying to predict which of 4 lights will turn on when she presses the button. And the other one is a circle of lights where the effort on the part of the participant in the experiment is to make the lights move around to the right or to the left. And in both these cases, Helmut found that people could succeed at this task, even though the source of the movement, or the source of selecting these 4 lights was really very completely random. It's theoretically random kinds of devices. I started in the field in 1980 in the Pear Lab at Princeton University, where we basically, in some sense, started doing replications of the kinds of experiments that Helmut had started. We had quite a number of different machines. They all had some sort of random process in the middle. In the upper right is perhaps you can see it, a pretty large drum from the American Southwest. And the drum beat was controlled by a random number generator, so it was irregular. It wasn't rhythmic the way it was supposed to be. And we surmised that if people had to listen to this uneven drum beat, rhythmic, they'd be motivated to fix it. And so they would move the random sequence closer to a smooth and proper one. We had a fountain. You can't see it very well in this picture, but it was a rather beautiful thing. It had a smooth stream of water that would at some point break up into droplets. And we asked people to try to change the point at which this breakup would occur. Keep it smooth longer or decrease the length of the smooth part of the channel. This, oops, sorry, I didn't need to move on. In the bottom is a linear pendulum. It's actually a beautiful thing. It belongs in an art museum. It has a clear plastic case, which is essentially airtight. It has a crystal ball at the bottom and a crystal rod this long. Very good bearings. And the object in this experiment was for the participant to keep that pendulum swinging as long as possible, or in the opposite condition, to slow it down as if the air got more dense. We had a chip experiment that used the same kind of devices that are in anybody's computer. We provided it with voltage that was just barely adequate to keep it from making errors. And we set it on a knife edge and asked people to make more errors, less errors. Lots of these things were complicated, hard to control, and so forth. But most of these experiments showed pretty much the same kind of results. Later I'll talk more about this upper left one, the random event generator, or random number generator. But here's a picture of the data from the pendulum experiment. It should be kind of, it should follow a kind of wandering path with a level trend, but you can see that it doesn't. And that's because the data that come out of the system, the measurements that we make of the pendulum are actually different from what's expected by chance, or what's expected from a normal pendulum just moving through air. Another experiment, this one's actually, some people would say it's macroscopic because it's a little more than 3 meters tall and 2 meters wide. It has 9,000 plastic marbles about this big. And they are brought to the top and then fall through an array of pins. They bounce around, and they tend to bounce a little to the left or a little to the right. And sometimes they make several steps to the right, and they'll end up being counted in a bin that's on the right side. And similar for the other side, the result is a kind of Gaussian or bell curve that we're used to from statistics. And you can see, again, in the data picture that whereas the baseline or normal behavior of data like this should be level, a level trend, what we get instead of that is pretty strong deviations. These experiments, most of them took place over years. This is what we call the benchmark REG. It's a pretty big thing, almost the size of this. Sitting on a table, somebody sits in a comfortable chair nearby, and their instruction is to get high numbers or low numbers. And it turns out that, somewhat surprisingly, at least from the point of view of understanding how these things work, when they want high numbers, they get high numbers. When they are trying for low numbers, it turns out they get low numbers. I'd like to show you just a little bit of what a random number generator is based upon, the kind of electronic ones we use. This is a picture of a diode, and it's put into a circuit where the current flow is banging up or meeting that barrier. And it turns out, perhaps you can see just a very small glow on the right-hand side. What happens is that through a process called electron tunneling, even though there's a barrier, even though it's a switch and it shouldn't allow any electrons to flow through, by the process of quantum tunneling, some electrons do pass through the barrier. They create a tiny voltage, which we measure, and we turn those, the high into a 1 and the low into 0. And the result is a random sequence that's really very much, very high, very clearly a random sequence of numbers, because the original source is itself unpredictable. It's a quantum level phenomenon, and by the nature of the process, it's just not possible to know whether the next bit or binary digit that comes through will be a 0 or 1. So in other words, these are really high quality random number generators that are used in this kind of experiment. This shows a little bit what the raw data would look like. You can't see any pattern, I'm sure. But if we do statistics and flip 200 coins, that is, take 200 bits and ask what's the sum of the 200 bits, how many ones are there, we get a distribution. So most of the time it's rather close to 100, which you would expect if it's truly random. And occasionally it goes a little high to out as far as perhaps 130 or so, and also in the other direction. And there's not very much pattern to see. So what we generally do to display data in these experiments is to make a graph that we call a cumulative deviation graph. Here you see the history of these numbers presented as a cumulative sum. It goes up, or that means the number was, the deviation was positive. If the line goes down, it means perhaps a sequence of negative numbers. But in this example, there isn't a clear trend at all. It's still basically acting randomly. This is the result using that big suitcase-sized machine over several years with 33 different people who came in to try to do to work their will to envision high numbers and low numbers and hopefully succeed in changing the behavior of this device. I think you can easily see that when they're trying for the high numbers, they succeeded. Similarly for the low numbers, and in our experiments we always had a third condition where we told people just let the machine do what it does. And typically, when we interviewed people afterward, they said, oh yes, I tried to get baseline numbers. I tried to get exactly 100. And they succeeded in that too, apparently. So over the years, as technology changed, by the 1990s, we were making much smaller random number generators. This is about this long. And this is one developed in Amsterdam by Dick Bierman and Joop Houtcooper, whom many of you know. These are designed to be used in systems that produce a continuous sequence of data, which we can mark in an index to show the beginning and the end of a period of time in which we're interested. What we're working up to is taking this kind of experiment out into the field, asking not only in the laboratory, but outside, perhaps at a concert or some kind of a ceremony, in a cathedral, for example. Might there be a gathering of consciousness in the group of people participating in a ritual or all enjoying an amazingly powerful concert? Might they come together as a kind of group consciousness? So we asked that question in a series of what we call field REG experiments, or field RNG experiments. Basically what we're looking for is kind of situations that create some kind of feeling of resonance or coherence among the people, that everybody kind of comes together and relates to each other, whether they're conscious of that directly or not. But we're brought, if it's music or if it's a ritual, we're brought into a common focus. So the idea was that in that case, we would see perhaps that a random number generator became part of the group and changed its behavior. We also did what you could think of as control experiments, where we would go to a busy street corner where you don't expect any kind of a group consciousness to develop. Here are just a couple of examples of that field RNG research. This isn't quite the natural stuff that people have explored in the early years of parapsychology, but it is back out into real life, into situations that are maybe special, but it is perhaps an indication that this evidence for psychic presence or psychic activity that we see in the laboratory isn't confined to the laboratory. So in Wyoming, there's a remarkable natural monument. It's the core of a volcano that remains after the mountain was eroded away. It's a sacred place for some of the Native American people. And we traveled around that with a shaman from the Shoshone tribe who was looking for a place to do a ceremony. His mission in life was to do healing ceremonies for sacred places that have been damaged in some psychological or archaeological way by misbehaving humans or misunderstanding people. You can see once again the expected line would be level, but it's definitely not. And even though he didn't know anything about the technology of the field, when he saw that graph, he said, "Ah, now I know what you mean." And in the right-hand figure, I had the great privilege and joy of traveling in Egypt with a pretty good number, 19 other people who were interested in the ancient religion. And we went to all the temples we could, and we planned to do meditations and maybe chanting in the Holy of Holies in each of those places. We also went to the Great Pyramid in Giza. And this very first segment shows this continuous random data from the miniaturized device with a palm-top computer as we were going into the pyramid. It's level and flat as usual. But when we got to the Queen's Chamber and to the Grand Gallery, go there if you can sometime, the data become extremely different from what's expected by chance. And then in the King's Chamber, we did 2 long meditations, and there too, the data were different from what's expected, random numbers.
Excuse me.
And then the last part of the graph shows, yes.
So you try to influence the numbers of the random number generator? Is that what you
Well, I'm carrying a small random number generator connected to a computer that's recording a continuous stream of random numbers.
So you try to get more ones once you
Actually,
enter?
it's a very good question. In these field experiments, nobody is trying to do anything to the random number generator. Instead, people are maybe, I guess the best way to put it is engaged in what is before them. So while we were in the Grand Gallery, we were chanting or meditating or whatever it was that seemed right to do. And almost everybody, actually even including me, forgot that there was a random number generator. And we didn't care. We were actually much more interested in the kind of regathering of ancient spiritual energies. Is that answering the question? Yeah, where nobody's trying.
And the numbers started to deviate while not trying too much.
Right. And in many of these so-called field RNG experiments, the audience, for example, at an opera, didn't even know there was a machine in the house. So, and yet we believe they're coming together as a group, enjoying the aria, actually made the atmosphere different somehow. And I don't have an explanation in technical terms, but I think it is pretty clear that the random number generator becomes part of that group. It's integrated into that group somehow. That's anthropomorphic, but it may be true. So we began to think about doing the same kind of thing, but on a larger scale. And a few prototype events came along, and this one, when Princess Diana was killed, we weren't running any data, continuous data at that time. But when her funeral was announced, and people all over the world were were interested in that. We decided that that would be a good example of a kind of global consciousness where millions and millions, some say a billion or more people, were focused on this, the events of the day of that funeral. At the top is the red line showing the actual data. That goes far enough from what's expected to be, to occur by chance, only once in 100 times for repetitions of such an experiment. The green lines are just simulations. And so we were encouraged to build a, what you might think of as permanent network of random number generators. And by the way, I don't know if Mario is still here. Mario was a host for one of those, but my friend Giannis from Greece, from Athens, in fact, has also hosted one of these devices for many years. And this shows where they were placed. There never were as many as, but this shows all of them that ever were part of the network. So we got a fairly widespread coverage in the world. This is just a picture of what the data look like when they're arriving at the server in Princeton. A mess. But our means of statistical processing allow us to make sense of those numbers and make them actually, and do the statistics to find out if there's anything different from just chance behavior. And we have a hypothesis in what's called the Global Consciousness Project, which is stated here in, thanks, by the way, to Marilena, in excellent Greek. Events which focus attention and emotion, and is shared by people all over the world, will correlate with changes in the data from our network of random number generators. I bet that's exactly what it says there. But alas, I have not yet learned enough Greek to find out. So we have basically created a kind of instrument. You comprise of all these maybe 50 or 60 random number generators at a given time. And it allows us to create a continuous, day after day, 24/7 record of random data, which is a combination of data from all these instruments spread around the world. And we can think of that as a kind of history of random data. And we, in principle, can compare that with the history of events in the world. So what we do in to do the specific, well-controlled hypothesis test is to select events in the world that we think will cause this kind of coherence among large numbers of people. So natural disasters, terrible accidents of various kinds, warlike acts and terrorist things, but also some more pleasant kinds of events, great celebrations such as New Year's or the Cumulative in India, where millions of people gather. Web-organized meditations and demonstrations that, again, bring very large numbers of people into the same frame of mind in a kind of synchronized way. So we have the possibility of quite a few different kinds of events where we can take the data, make the prediction that the data will not be random. I'm showing you first here a case where the data can't be distinguished from just an ordinary random walk. This is what the data should look like if nothing ever happened. Then we move on to an example of what the data look like when they change in correlation with the event in the world. We're talking about dealing with what we think of as a low signal-to-noise ratio system. In other words, there's not very much signal, and it's usually mostly buried in noise. So the statistics allows us to gradually build up a database which we can think of as replications, one after another, of the same basic question. And it turns out that in more than half, almost 70% of the events that we have looked at, the outcome is in the direction we predict. And quite a few of those, again, almost 20%, are nominally significant. They reach the 5% level, which is represented in these graphs by that blue smooth curve. I'll give you a couple of examples. This one is, without question, the most impressive in our database. September 11, 2001, the world was shocked and really probably very sharply focused and brought into a kind of resonant frame of mind. Wasn't necessarily that everybody was happy, not at all, but we were paying attention in a kind of synchronized manner to what happened and what was happening during that time. So this shows a picture, the same kind I showed before, but this now covers a period of 9 days with 9/11 in the middle. As you can see, on the left is what I've been describing as a normal random walk. That's what we expect the data to look like. But in the middle, sometime around September 11th, it takes a trend which is extreme. It's very strong and persists for about 3 days. And we can't say exactly where it begins, but it looks like it might even begin a little bit, early relative to the events. And then after 3 days, it becomes normal again. We process that further. It would just continue to look like more of the same, just random. We looked at this event in many different ways. We had some formal predictions and some less, we did some informal analysis too, just to try to understand more what was going on. This is a different measure, it's independent, and it shows also a very strong difference from expectation right around the time of the event. And on both sides, it's random. It's what we expect. In Japan in 2011, we undoubtedly all remember there was this enormous earthquake, Richter 9 something, and a tsunami that destroyed Fukushima and made a mess of the reactors there, and we're still seeing results from that. Again, different ways of looking at the data. Some displays. This one covers 48 hours. This is the quake itself, but this probably corresponds to some part of the realization of how big a disaster this was. Again, because it's a low signal to noise system, we don't even know whether those are real representations of what the data do or there's something else. Here's another using a different algorithm. This is by Dean Radin, who many of you know. The analysis, again, shows a really big change, highly significant change right around the time of the event. We also, I mentioned, we do positive events as well, and this is the Cumulative that I mentioned, where something on the order of 10 million, and in the major years, as many as 20 million people may gather in the Ganges to wash away all their sin. These aren't highly significant, but they are so similar over a number of years that they become a little more persuasive just for that reason. And we do these organized meditations and gatherings of as many people as possible to work for peace, to pray for peace, and so on. We don't always win. Sometimes the data are just random. And on the other hand, there's a majority of these kinds of events seem to show that when people gather intentionally to demonstrate or to pray for peace or whatever, it produces an effect of the sort that one of my colleagues, Brian Wilson terms global harmony events. he went through the database and found as many as he could of events that are not prayer necessarily or demonstration, but a variety of things that fit into that general positive mode, and put them all together, more than 100 here, and they show a really strong, clear indication. The likelihood of that happening just by chance over these many years is very small, a few parts in 10,000. So coming to toward the end of the talk, this is the picture of all the data that we did until December 2015, cut off the formal experiments in late December 2015, and there are 500 events exactly. And probably for most of you, certainly it's true for me, that, again, doesn't show much pattern. But if you do the statistics, you find that this dotted line here is the expectation. Just above that, separated by a small amount, is the average of the actual data. And it turns out that that difference is highly significant. The probability, the z-score, or the number of sigmas deviation, is around 7. And the probability is many zeros, 13, 12 zeros, and then a 1. But this is a picture where you can see the same data now displayed in the way I've been displaying these individual experiments, where each point in the graph is if it's positive, the line goes up. If it's negative outcome, the line goes down. You can see here a period where not much was happening. But the general trend is for the outcome of these experiments to match the prediction so strongly that, again, in 500 replications of this specific experiment, we have a z-score of 7. That means the departure is as big as people in physics and most of the hard sciences consider to be quite impressive. 6 or 7 sigma usually means it's real. But of course, in parapsychology, it means that we still have to try to convince them. And again, the probability is 10 to the minus 13. Just in case some of you are worried that our machine doesn't work right, this is the kind of a cloud of simulations, or you can think of the extractions from the data when there is no event that we've identified. About 98% of the data don't have one of our events in it. And that's the kind of outcome you get if you put the same set of event definitions on the data stream, but not where the events were. And you do that repeatedly, you get a pretty good indication of what random behavior or what the natural behavior of the system would be. And you can see that our data line is definitely not part of that distribution. So a couple of kind of comprehensive looks. It's interesting to discover that if we don't consider the events but look at the data stream as a whole, it has a bit of a shape, especially this long trend here. We can do calculations to discover that it's actually a significant trend. It's not just chance. And it turns out that this whole period of time corresponds with one of our American presidential administrations, and then it begins to change as a different president takes over, as Bush and Obama. For what it's worth, I'll show you a kind of addition to this graph, which is a picture of the presidential approval ratings, which is, we don't have it for the whole period of time, but you can see that there's a rather nice match in a way. And it almost looks like, well, the presidential approval rating it affects our data, or that they're very closely correlated. But I have to show you a different picture. This is the same data, but now we overlay that or compare it with the dollar index. That's how much is the dollar worth compared to other currencies. Some guy who was interested in that kind of thing said, your code looks so familiar to me. And he discovered this dollar index is in fact so similar that he decided that they must be correlated. And in some sort of general pictorial way they're correlated. It's not an attempt to explain. In a way, it's a kind of an object lesson in how easy it is to discover correlations that might not be meaningful. We don't know whether it's meaningful or not without doing a formal experiment. Here are some other kinds of ways of looking at the data in a comprehensive sense. This is not a surprising thing, but it's good the data show that if there are more people in an event, if it's a bigger event, because it's important or whatever, the effect size will be larger. And here's one that I like even more. If the events that we are looking at and, can be rated as to how much they evoke compassion, how much compassion is really involved in the event, then we get bigger effects. It's actually a significant difference. This is the high level of compassion compared with the low level of compassion. Many events don't have any way of being rated as to compassion, but I think that's nice because in a way compassion represents the thing that I believe the experiment is about. That we are interconnected in some sense. And when we gather in groups and synchronize our emotions, we become more connected with each other. Compassion is an automatic emotion that allows us or is created when we connect with each other. It's not something you do by yourself. Compassion requires other people. Here's one that's very interesting. This is a figure created by Peter Mansell, a colleague in Paris. It basically, without going into a lot of detail, shows that when we are asleep, the effect size in these events gets small. When we're awake, it's larger. That shouldn't be a surprise, of course, if we want to talk about consciousness, even if it's unconscious consciousness, we should be thinking that awake is part of the consciousness. And on the bottom is the same kind of data, but during the control period. So I think there's evidence, and I'll show this in brief, but basically, I think the evidence, not just from my experiments or the ones of the Pear Lab, but those going back to Tanagras and Bender and so many scientists who have tried hard to find out if there is any kind of a connection of people, our consciousness, our attentions, and so forth, with the external world, with the environment. The experiments are showing that mind is not, it's not stuck inside your head. Mind extends out into the world, and it apparently has effects. So what we wish for or what we intend is a little bit more likely than if we didn't wish for it. It may be, as Mario said, a very small effect, but it's probably more important than we have understood up to now. And what I hope that we may take away and develop in the future is a deeper understanding of the interconnection of people with each other and with the world in such a way that we'll actually begin to take care of the world instead of dominating it, and we might become the caretakers of our rather beautiful world, of which Greece is an especially beautiful part. Thank you. Yes.
Dr. Nelson, would you happen to have recorded in your generators 2 years ago here in Greece, we were at the fringe of Brexit. Greece was almost fallen out of the euro. Did you have any recordings of this issue?
Well,
it would be really interesting.
the answer is Yes. So because we do continuously report, we have data for every day for almost 20 years. So we have that period of time. In order to ask the kind of question and get the kinds of answers I've been presenting here, we have to make a specific question. We have to know when the time of interest begins and when it ends exactly, so we can make a prediction about that period of time, the data collected then. And sometimes it shows really quite remarkable and surprising things. Maybe you can give me the exact dates you think would be.
We could, yes. It's
Yeah.
close.
And I can take a look, and if I have your email address, I can even send you a picture. Yeah.
I have a question. You have events happening all the time, obviously. So do you have any type of correlation between the amplitude of the events, of the number of people involved, and the effect size that you actually look at? Any type of correlation?
Yes.
And also another question would be, is there any minimum number of people that have to be involved so that you can see some type of effect on your spectrum?
It's a good question, and the answer is yes, although we don't understand it, in a very strong way. We know that if we have, if we can document that there are many, many millions of people, hundreds of millions, who are involved in thinking about the event, that will produce a stronger effect than if there are only 100,000 or 10,000 people. Sometimes people write to me and say, I'm gathering my friends and we're going to have a prayer ceremony. Can you record what happens? So I have to disappoint them and say that the system really is designed to look at global issues. That means that we really need to have a large number of people spread around the globe. Yeah.
Roger, I was just wondering during your talk, can we turn around by saying, looking at the signal, selecting the large deviations, and then go back and say, has there been a large
Right.
global event?
Right.
Of course, there are always large events, but
Yes, there are.
has there been done anything like that?
Well, the truth is, I and most of my colleagues are pretty sure that we can't do a good scientific experiment that way because the world is too big and complicated. So if we pick out a spike of data and say, what corresponds to that, we could probably find a dozen things or 100 things because there is something happening everywhere all the time. So we have to do it the way we do to make a prediction before we know anything about the data and make it very specific so there's no slippage at all. And we take our chances. Sometimes, as I mentioned, our prediction isn't borne out. In fact, at least 30% of the time, we're, you might say, wrong. But the other problem is, of course, that the noisiness of the system requires, and this would address your question also to some degree, requires that we do many repetitions because any given picture of the data from one event will be largely noise, and we only will find out if that kind of event produces an effect that we parse by building up the evidence, the structured part of the data, and letting the random stuff wash out. So in other words, we need replication. We don't think we can make any kind of declarations about events unless we have 10 or a dozen or 24 events of a similar kind.
So no reverse engineering?
No, I mean, people are welcome. The data are always available online, and people are welcome to, locate a spike and see if they can figure out what it belongs to, but we wouldn't be able to draw a scientific conclusion about it.
Can you put like a random number generator, like somewhere like the Acropolis where the energy itself has its own like energy? Would it work there? Or?
Can somebody repeat that?
If you can put RG in the Acropolis to see if the energy is there, but that's what you did with the, now it's the people.
Would it work in a more like a place that has its own energy, or would it need to be somewhere like outside of like in North Modern?
I have a sort of suspicion, that is to say, a weak case to make for the fact that a sacred place, like the Parthenon.
Or like Wyoming that you mentioned earlier, like anywhere that has its...
Yeah. When we traveled in Egypt, we went to cities and bazaars and all of that, as well as to sacred places, the temples and so on. And the difference was we made a kind of weak prediction that we would see larger effects when we were in a holy place, like the temple, Holy of Holies, and it turned out that way.
But Roger, those were, that was a different experiment.
Yeah.
The one now is, those were sacred places. Now it's events that a lot of people know about, like an earthquake,
Right.
where we all
Right, so...
talk about New Year's and earthquakes in the oceans where nobody is.
Oh, okay. Fortunately, my wife knows my work better than I do. Again, one of it was Peter Bancel, the same one that did this time of day thing. He gathered, I believe it was 600 big earthquakes. 500 were in the oceans. And only about 100 were on land. They were the kind of Richter magnitude 6 and more that caused damage and often death. And what he found was a pattern in the ones that were on land and where there was destruction and death. Starting well before the earthquake, a few hours, the data, a certain kind of data went down and it got to the lowest point at the time of the earthquake, and then came back up again. In other words, kind of V-shaped surrounding earthquake. In the ocean, nothing, no pattern at all, because apparently the whales and fish don't care.
So we have no much time for more questions, so thank you
Okay.
again, Roger. And